Hello everyone and welcome. In this video we're going to look at the following problem. So we want to examine the convergence, and if the integral is convergent we're going to determine its value. So the integral is the integral from 0 to 1 of ln of x over x minus 1 dx. Now for reference we're going to denote it by I. Okay, let's start with the convergence. Now we are going to define the function f by f of x equals the integrand for x between 0 and 1, and f of 1 is equal to 1. Now of course this function is continuous on the interval open at 0, close at 1, and this is because the limit of natural log of x over x minus 1 as x approaches 0 from the right is plus infinity, and the limit of the same quantity as x approaches 1 from the left is 1. Okay, now we are going to choose a number p between 0 and 1, and we're going to also choose a positive constant c. Now we know that the limit of x to the p times natural log of x is equal to 0. So if we divide it by x minus 1, the limit won't change. So the limit of x to the p times f of x as x approaches 0 from the right is equal to 0. Now using the epsilon delta definition of the limit with epsilon equals c, we can guarantee that there exists a positive number a, and we're going to assume that that number is actually between 0 and 1, such that x to the p times f of x is less than or equal to c as long as x is between 0 and a. Now, because x is different from 0, we can divide both sides by x to the p, and we end up with the following. So f of x is positive and less than or equal to c over x to the p as long as x is between 0 and a. Now we're going to look at the integral of f. Now the integral of f from 0 to 1 is the integral from 0 to a plus the integral from a to 1. Now from a to 1, we have an upper bound for f. So f is bounded above by c over x to the p. Now, if we look at the first integral, because p is between 0 and 1, we know that the first integral converges. And the second integral converges as well, because f is continuous from a to 1. So this shows that the integral from 0 to 1 of f of x dx converges. Now we're going to compute the value of the integral. I'm going to present two different approaches. In the first approach, I'm going to use power series. Okay, so I am going to make a change of variable first. I'm going to substitute t equals 1 minus x. So of course this is going to give us that I is equal to negative integral from 0 to 1 of natural log of 1 minus t over t dt. And then we use the power series of natural log of 1 minus t around 0. And that power series is given by the following sum, and it converges for t between negative 1 included and 1 excluded. So now if we replace, we're going to get that I is equal to negative integral from 0 to 1 of negative 1 over t, sum as n goes from 1 to plus infinity of t to the n over n dt. Now we can divide t to the n by t, And we can also multiply the two minuses. So minus by minus, just plus. So we get that I is equal to integral from 0 to 1 of the sum as n goes from 1 to infinity of t to the n minus 1 over n dt. Now, we have an improper integral at 1 because if you look at this series, it does not converge for t equals 1. If we take the limit of our series as t goes to 1 from the left, we're going to get the harmonic series. So we have divergence. Now, how do we avoid that? Well, we're going to consider this as an improper integral. And in order to compute it, we're going to take the limit as b approaches 1 from the left of the integral from 0 to b of the sum as n goes from 1 to infinity of t to the n minus 1 over n dt. Now, because this series is convergent from -1 included to 1 excluded, we know that the interval 0 to b, as long as b is less than 1, is contained in the interval of convergence. We can then switch the summation and the integration. So let's do that. We can switch and then we can integrate. As we integrate, we get the limit as b approaches 1 from the left of the sum as n goes from 1 to infinity of t to the n over n squared. Now we're going to evaluate this between 0 and b. Now as we evaluate this at 0, we get 0. Evaluate at b, we get the sum as n goes from 1 to infinity of b to the n over n squared. Now, this is a convergent series. The series converges even for b equals 1. So we can simply take the limit. As we take the limit, we get that I is equal to the sum as n goes from 1 to infinity of 1 over n squared. And this is exactly zeta of 2. This is the Basel problem. And zeta of 2 is equal to pi squared over 6. Now, quickly, I'm going to present another approach to get the same answer. So to get the same answer, after making a change of variable, so we saw that I was equal to negative integral from 0 to 1 of the natural log of 1 minus x over x dx. So the idea here is to look at this as a special function, and that function is the Dilogarithm function. So this is equal to the Dilogarithm function evaluated at 1. And as we evaluate the Dilogarithm at 1, we get exactly zeta of 2. And zeta of 2 is precisely pi squared over 6. Now, we've reached the end of our video. Thank you for watching. Please consider subscribing, liking, sharing, and commenting. And I'll see you next time. Bye.